Welcome back to the course on two-phase flow with phase change in conventional and miniature channels. We were discussing the modeling of two-phase flow. In that, we have discussed the homogeneous model and then the separated flow model with Lockhart-Martinelli correlation. Today, we will continue the discussion of separated flow model with another correlation, Martinelli and Nelson correlation, and after that we will solve some numerical examples with Lockhart-Martinelli correlation and Martinelli and Nelson correlation. The Martinelli and Nelson correlation was obtained from Lockhart-Martinelli correlation, and it was developed for pressure drop in boiling channels. It applies to steam water mixture at all pressures between the atmospheric pressure and the critical pressure, which is approximately 221 bar. And this is of very much practical use, because steam water mixture is used in many industrial applications like boilers and under boiling conditions as well as condensing conditions. The air water data of Lockhart and Martinelli, it was assumed to represent steam water mixture at atmospheric pressure, and at the critical pressure we know that there is no distinction between liquid and gas. So, therefore, in the expression for phi FO square, if we put rho f is equal to rho g, mu f equal to mu g, etc., then and in xtt also. So, then what we get? We get phi FO square equal to 1 and xtt is equal to 1 minus x upon x raised to 0.875. Lockhart and Martinelli assumed turbulent regime, which exists in most of the industrial applications involving conventional channels. As we will see in the numerical examples, in case of conventional channels with realistic values, we will get both phases as turbulent. Then they plotted phi FO square as a function of xtt for p equal to 1 bar and p equal to p critical. And then for intermediate pressures, they interpolated. Now, how did they get phi FO square? So, Lockhart-Martinelli correlation gives phi f square, and Martinelli-Nelson have used phi FO square because phi FO square is more convenient in case of boiling or condensing channels, because the local quality is difficult to know, but the overall flow rate is known. As you can see in phi FO square, in the expression for in dP by dz f FO, when we want to evaluate, there is no x here, but in this dP by dz f comma f, in this there is local quality is involved. So, to calculate this quantity, we will need to know local quality, whereas to calculate this pressure gradient, we do not need any local quality. So, this pressure gradient is easier to evaluate in case of boiling channels, and therefore, it is more convenient to use phi FO square. So, how do we obtain phi FO square from phi f square? For that, we can derive a relation. Phi FO square, we have derived this earlier. Phi FO square is given by this, and phi f square is given by this expression, and then if we take the ratio, then we get this relation between phi FO square and phi f square. And now, we need this, the ratio of the friction factors. So, since it is turbulent regime, using that we get FFO and FF, and then we take the ratio, and then we get this expression. So, they got phi FO square for atmospheric pressure as well as critical pressure, and then by interpolation they got phi FO square for intermediate pressures. This is the graph given by Martinelli and Nelson, and here we have on the horizontal axis we have mass quality, on the vertical axis we have phi FO square, and these are for different pressures. This is for atmospheric pressure, and then we have higher pressure and still higher pressures up to very high pressures. Here we have the same data in the form of tables. So, by knowing the quality and the pressure, we can get phi FO square. Martinelli and Nelson also plotted the Voigt fraction alpha, again in a similar method. They got alpha for atmospheric pressure using Lockhart-Martinelli correlation, and for critical pressure there is no distinction between the phases. So, and then by interpolation they got for the intermediate pressures. So, we have mass quality on the horizontal axis, Voigt fraction on the vertical axis. The horizontal scale is logarithmic, it is a semi-log plot, and we have alpha for different pressures. So, for horizontal, for atmospheric pressure and higher pressures and very high pressures. Actually, we should sketch the plot of alpha versus x on a linear scale to see how it varies. It will be like this. Zero, 1, and here it is 0, 1, here we have alpha. At x equal to 0, alpha is equal to 0, and at x equal to 1, alpha is equal to 1, but it does not vary like that, does not vary linearly. At critical pressure, we get a linear graph, but at lower pressures, we get this type of variation. Okay. So, for low values of x, as x increases, alpha increases very fast. The slope is high, delta alpha by delta x. At constant pressure, this is the slope of the curve, and this is very high for low values of x. And for higher values of x, the slope decreases, and then for very high values of x, the slope is very low. But for very high values, even for not so high values of x, alpha becomes very close to 1. Okay. So, now how to calculate pressure gradient due to acceleration and gravity? For pressure gradient due to acceleration and gravity, we need the Voigt fraction and its partial derivatives. The Voigt fraction alpha is given by this, the fundamental Voigt quality relation, which we have derived before in the first lecture, and this quantity, the ratio of the velocities of the phases is called the slip ratio S, and usually S is greater than 1. For HEM, we assume that both phases move with the same velocity. So, S is equal to 1, and in separated flow model we account for the difference of velocities, and S is usually greater than 1. In horizontal flow as well as vertical upward flow, gas will move faster and liquid will move slower. So, slip ratio will be greater than 1. Now, if we put S equal to 1, then the void fraction that we get is the volumetric quality, and 1 minus beta upon beta is equal to this expression, and if we solve for beta, we get this expression. From this we can calculate beta, and here this expression, this is 1 minus beta upon beta. So, we get 1 minus alpha upon alpha is equal to 1 minus beta upon beta into S. For homogeneous model, S equal to 1. So, we get alpha equal to beta, and for separated flow model, S is greater than 1. So, alpha should be less than beta. Now, if we use the Lockhart-Martinelli correlation, then we can find alpha from the graphs given by Lockhart-Martinelli, or we can use a correlation, for example, the Butterworth correlation. This was obtained by fitting the graphs of Lockhart and Martinelli, and beta can be obtained from this expression, and then we should check whether alpha is less than beta or not. Now, depending on the flow regime, we can find capital X. To capital X, the Martinelli parameter XVV is equal to this, and XTT is given by this expression, as we know. And then by substituting the appropriate correlation here, we can express alpha in terms of properties and the quality. So, we get alpha as a function of pressure and quality, and then we need this partial derivative delta alpha by delta x at constant pressure. So, this, as I have just explained, by finding the slope of the graph of alpha versus x for a constant pressure, we can get the value of this partial derivative. Or if we are not using graph, but using a correlation like this correlation, then we differentiate it after substituting for the Martinelli parameter. We differentiate with respect to quality, and by using the chain rule, by multiplying these two derivatives, we get the this derivative. Okay. And then we substitute it here and get V star, and then using the value of V star here, we get the pressure gradient due to acceleration. M square has to be evaluated. For that, there is a long and complicated expression. So, in this course, we will calculate M square from homogeneous model and use the same as M square here also as a rough estimate. But for a more accurate calculation, M square has to be obtained using the expression for separated flow model. Now, this alpha in the pressure gradient due to gravity, this alpha can be substituted, and then we can get the pressure gradient due to gravity. Okay. Now, if we use Martinelli-Nelson correlation, then we can get alpha from graph for a given quality and pressure, and then by finding the slope of the graph, we can get this partial derivative by taking two nearby values of the quality and corresponding values of the Voigt fraction, and then dividing, we can get this partial derivative, and then substitute it here and calculate V star, then substitute V star here and calculate the pressure gradient due to acceleration. The pressure gradient due to gravity can be calculated by using the Voigt fraction obtained from the graph. Now, let us consider some numerical examples using Lockhart-Martinelli correlation. Here the data is the same as that we used for the homogeneous model. In the first problem, it is water steam mixture at 100 kilopascal pressure and horizontal flow, diameter is 2 mm and length is 10 centimeter, mass flux is 100 kg per meter square second, inlet quality is 0 and the heat flux is 20 kilowatt per meter square, and we have to find the pressure gradient at the midpoint z equal to 5 centimeter. So, properties are same as we have used before. Dx by dz is obtained using energy balance and it is the same as before. dVg by dP is obtained by numerical differentiation. We take two nearby values of pressure, 100 kilopascal and 101 kilopascal, and corresponding values of Vg. This is Vg at 100 kilopascal and this is the Vg at 101 kilopascal, and we take the difference of these two and divide by the pressure difference, and then we get this dVg by dP. Then we calculate m square. So, here we are using the expression of m square as the same as that for the homogeneous model, because the expression for separated flow model is very complicated and it involves a partial derivative with respect to pressure, which is very difficult to obtain either from the graphs or from the equations. In this case, m square is much less than 1. So, therefore, 1 minus m square is approximately equal to 1 and 1 upon 1 minus m square is also approximately equal to 1. Suppose we are able to calculate the accurate value of m square from the expression for separated flow model, then also it is likely to be of the same order of magnitude. This is of the order of 10 raised to minus 3. So, it will be negligible with respect to 1, and therefore, 1 minus m square can be taken as approximately equal to 1. Now, REF is 691 and it is laminar, REG is 360, so it is laminar, and therefore, we get FF using the expression for laminar flow is 0.023 and Fg also for laminar flow is calculated as 0.044. Now, since both phases are laminar in this case, it is the viscous regime, and therefore, we calculate XVV using this expression, we get a 0.793. For Voigt fraction, we can use Lockhart-Martinelli graphs but here we are using the correlation given by Butterworth. In this we substitute the value of Martinelli parameter and we get alpha equal to 0.808 and beta is obtained as 0.973, and we can check here that alpha is less than beta as expected. Then we use the Shishal-Laird relations. Again, for phi g square or phi f square we could have used graphs, but here we are using Shishal-Laird relations, and with C is equal to 5 for viscous regime, C is equal to 5, and therefore we get phi g square 5.59 and phi f square 8.9, and then we calculate this frictional pressure gradient. If we use phi f square, we get 2.05 kilopascal per meter, and if we use phi g square, then also we get the same value 2.05 kilopascal per meter. So, therefore, we can be assured that the calculations are correct. Now, the pressure gradient due to acceleration is given by this expression, and 1 minus m square is approximately equal to 1. So, V star is given by this expression here. Alpha is given by the Butterworth expression, XVV is given by this, and if we substitute it, we get alpha as a function of x, the quality, and we differentiate to find the slope. So, we get this expression, and this partial derivative is calculated from the expression for Martinelli parameter, and it is equal to this. And therefore, finally, we get the partial derivative of alpha with respect to x as 5.97, and substituting this here, we get V star as 0.236 meter cube per kg, and then substituting this value of V star, we get the pressure gradient due to acceleration as 1.045 kilopascal per meter. So, pressure gradient due to friction is this 2.054 kilopascal per meter. Pressure gradient due to acceleration is 1.05 kilopascal per meter. Pressure gradient due to gravity is 0 because it is horizontal flow, and then we add all these pressure gradients and get this final value, total pressure gradient 3.10 kilopascal per meter. Now, here we have used the Butterworth relation for alpha, but you can use the graph and also do the same calculations using Lockhart-Martinelli graphs. For the frictional multiplier, we have used Shishal-Laird expressions, phi g square and phi f square, but instead of that you can use the Wilson relations, or you can use the graphs, original graphs of Lockhart and Martinelli, and repeat the calculation. Now, let us consider the second example. Here also the data is the same as the second example for homogeneous model, 100 kilopascal, vertical upward flow, diameter is 2 centimeter, length is 2 meter, mass flux is 1000 kg per meter square second, inlet quality is 0, outlet quality is 2%, and we have to find the pressure gradient at the midpoint, that is Z equal to 1 meter. Now, the properties at 100 kilopascal are the same as before. X at the midpoint is 1%, dx by dz is 0.01 per meter as before, and dVg by dP is obtained by numerical differentiation, and we get minus 1.57 into 10 raised to minus 5 meter cube per kg per Pascal. So, using this dVg by dP, we calculate m square using the expression for homogeneous model, and it is 0.157, and this is not negligible compared to unity. 1 minus m square is equal to 0.843, and 1 upon 1 minus m square is equal to 1.186. Now, here we have used the homogeneous expression for m square. If we use the separated flow expression, then we may get a different value, but since it is very complicated, in this example we are not using, but it can be done. The partial derivatives involved have to be calculated using numerical differentiation, and then a correction can be made. Now, Reynolds numbers for the phases are this 6.99 into 10 raised to 4. So, it is turbulent flow for the liquid phase, and for the gas phase Reynolds number is 1.63 into 10 raised to 4. So, this is also turbulent. So, we use the friction factor correlation for turbulent flow. Here we use Blasius relation, and we get friction factor FF as 4.86 into 10 raised to minus 3, and Fg is equal to 6.99 into 10 raised to minus 3. Okay. Now, since it is turbulent regime, we use the expression for xTT, which is calculated as 2.05, and alpha is calculated from Butterworth relation as 0.682, and beta is 0.942. So, here also we see that alpha is less than beta. For the frictional multipliers, we use the Shishal-Layard relations, and for turbulent regime, the value of C is 20, and using that we get phi g square equal to 46.1 and phi f square is equal to 11. Now, by substituting phi g square here, we get dP by dz f equal to 5.46 kilopascal per meter, and using phi f square again we get the frictional pressure gradient as the same 5.46 kilopascal per meter. Now, for the acceleration pressure gradient, this is the expression, and V star is given by this expression. So, to calculate V star, we have to find the partial derivative of alpha with respect to x. So, we use the Butterworth relation for alpha and relation for xTT and substitute it here, then we get d by alpha by d by x, and this is calculated as 20.8. The method is similar to that in the previous example, except that the expression for xTT is used here in place of xVV. So, V star is obtained as 0.246 meter cube per kg, and using this V star we get the pressure gradient due to acceleration as 2.92 kilopascal per meter. So, we have Pressure gradient due to friction is 5.46 kilopascal per meter. Pressure gradient due to acceleration is 2.92 kilopascal per meter, and pressure gradient due to gravity is calculated using this expression, and here the value of alpha obtained from the Butterworth correlation is used, and we get 2.99 kilopascal per meter. And when we add all these pressure gradients, we get the total pressure gradient as 11.37 kilopascal per meter. Now, let us consider the third example. Again, the data is same as that in the third example for homogeneous model. Pressure is 10 megapascal, it is vertical upward flow, and diameter is 2 centimeter, length is 2 meter. Mass flux is 1000 units, inlet quality is 0, outlet quality is 2%, and we have to find the pressure gradient at the midpoint, z equal to 1 meter. Now, at 10 megapascal pressure, these are the properties, the same as before. The quality is 1% at the midpoint, dx by dz is 0.01 per meter, dVg by dP is also the same as before, it is 2.20 into 10 raised to minus 9 meter cube per kg per Pascal. So, m square again is obtained from the homogeneous expression, and it is of the order of 10 raised to minus 5. So, it is negligible compared to unity. So, 1 minus m square is nearly equal to 1, and 1 upon 1 minus m square is also nearly equal to 1. The Reynolds number for the liquid phase is 2.42 into 10 raised to 5. So, it is turbulent. Reynolds number for the gas phase is 9866. So, this is also turbulent. So, it is the turbulent regime. Friction factor using Blasius equation is 3.56 into 10 raised to minus 3, and friction factor for the gas phase using Blasius relation is 7.93 into 10 raised to minus 3. Now, since it is turbulent regime, we use XTT, which is 18.8, and using this XTT we obtain alpha as 0.308, beta is 0.114. So, in this case we are getting alpha greater than beta. So, this needs to be checked. It is possible that Butterworth relation has some limitations, and it may be having some range of applicability, and this value of the Martinelli parameter might be outside its validity. You can use the graphs also and repeat the calculation and check whether you get similar results or different results. Now, for frictional multipliers, we use Shishorn-Layard relations, and C equal to 20 for turbulent regime. We get phi g square is equal to 730.44, phi f square is equal to 2.06. Frictional pressure gradient using phi f square is obtained as 1.047 kilopascal per meter, and using phi g square also we get the same value, 1.047 kilopascal per meter. Now, frictional pressure gradient due to acceleration has to be obtained, and for this we require V star. So, to calculate V star, we do a similar calculation. There should have been a comma here. and alpha is given by this expression, and then we have to obtain this partial derivative, and similar to the previous problem, we do the calculations and get delta alpha by delta x, which is 257, and then we substitute this value here and calculate V star, which is 0.756 meter cube per kg, and then we substitute this value and get the pressure gradient due to acceleration as 7.56 kilopascal per meter. So, pressure gradient due to friction is 1.047 kilopascal per meter, due to acceleration it is 7.56 kilopascal per meter, and pressure gradient due to gravity is calculated using this formula, and it is 4.83 kilopascal per meter. And after adding these pressure gradients, we get the total pressure gradient 13.44 kilopascal per meter. Okay. So, now consider some numerical examples using the Martinelli-Nelson correlation. Example 1, again the data is the same as that in the homogeneous model and the Lockhart-Martinelli correlation. Properties are the same, dx by dz is the same, dvg by dp is the same, and m square is negligible compared to unity. So, 1 upon 1 minus m square is nearly equal to 1. Then we obtain REFO, because for Martinelli-Nelson correlation we need FFO. So, REFO is 706, and so it is laminar flow, and for FFO we use the laminar flow relation, and it is 0.023. Note that the Martinelli-Nelson correlation was obtained by assuming turbulent flow regime, which is the regime which mostly exists in conventional channels in practical applications. But in this case it is laminar flow. In fact, both phases are laminar, but we are still trying to apply Martinelli-Nelson correlation and see what we get. So, now from the Martinelli-Nelson graphs we read the value of alpha, we know the pressure and the quality, and from that, from the graph we get the value of alpha as 0.73, and the value of beta is calculated at 0.973. Phi FO square is also obtained from the graph by knowing pressure and quality, and it is 12.98. When we substitute the value of phi FO square here and calculate the frictional pressure gradient, and we get it as 3.06 kilopascal per meter. Now, the pressure gradient due to acceleration has to be calculated, and it requires V star. So, to calculate V star we need the slope. So, again we look at the graph of alpha versus x for the corresponding pressure, and the slope of the graph at that point is nearly equal to 6. So, we substitute the slope here and calculate, and alpha we have already obtained. So, we calculate the value of V star, which is 0.1678 meter cube per kg, and then after substituting V star we get pressure gradient due to acceleration as 0.743 kilopascal per meter. So, pressure gradient due to friction is 3.06 kilopascal per meter, pressure gradient due to acceleration is 0.743 kilopascal per meter, pressure gradient due to gravity is 0, and the total pressure gradient by adding all of these is 3.8 kilopascal per meter. Now, let us consider the second example. The data is the same as in the second examples in the previous models. Properties are the same, x and dx by dz are the same, dvg by dt, dvg by dp is this, and m square in this case is 0.157, which is not negligible, and therefore 1 upon 1 minus m square is equal to 1.186. REFO is 706, so it is laminar flow, and we get FFO as 0.023. Alpha is read from the Martinelli-Nelson graphs for the given quality and pressure, and it is 0.67. Beta is calculated 0.943, and for this pressure and quality we read phi FO square from Martinelli-Nelson graphs, and it is 5.6. Then we substitute the value of phi FO square in the expression for the pressure gradient due to friction, and we get the result as 0.1322 kilopascal per meter. Then from the Voigt fraction graphs we obtain the slope delta alpha by delta x, which is equal to 6, and then we substitute this slope here, and we get V star as 0.098 meter cube per kg, and pressure gradient due to acceleration is obtained as 1.167 kilopascal per meter. So, we get frictional pressure gradient as 0.1322 kilopascal per meter, acceleration pressure gradient 1.167 kilopascal per meter, and the gravitational pressure gradient as 3.105 kilopascal per meter. Then when we add all these pressure gradients, we get the total pressure gradient as 4.40 kilopascal per meter. Now, let us consider the third example. Again, the data is the same as the corresponding third examples in the previous two models. The properties will be the same, x and dx by dz will be the same, dvg by dp will be the same, and m square is negligible. So, 1 upon 1 minus m square is nearly equal to 1. REFO is calculated as 2.44 into 10 raised to 5. So, it is turbulent flow, and FFO using the turbulent flow expression, the Blasius relation, we get 0.0036. Now, we read alpha from Martinelli-Nelson graphs for the given pressure and quality, and it is 0.1, and beta is calculated as 0.1114. So, alpha is less than beta, but it is only slightly less in this case. This is actually expected because the pressure is high. Therefore, the density of gas will be only slightly less than the density of liquid, and therefore, the density ratio will not be as large as at low pressures, and because of that the slip between the phases or the relative motion between the phases will be less, and so S, the value of the slip ratio, will not be very much different from unity. So, therefore, we can expect alpha to be only slightly less than beta. Now, phi FO square is read from the Martinelli-Nelson graphs for the given pressure and quality, and it is obtained as 1.35, and using this value of phi FO square, we get pressure gradient due to friction as 0.697 kilopascal per meter. The pressure gradient due to acceleration has to be calculated. For that, the slope of the alpha versus x graph is calculated, and it is 2, and then using this value of alpha, we calculate V star, which is 0.099 meter cube per kg, and using this value of V star, we get the pressure gradient due to acceleration as 0.035 kilopascal per meter. Now, xtt, since it is turbulent regime, we calculate xtt, which is 18.8. Okay. So, the pressure gradient due to friction is 0.697 kilopascal per meter. The pressure gradient due to acceleration is 0.035 kilopascal per meter, and the pressure gradient due to gravity is obtained using this expression, and it is 6.12 kilopascal per meter, and by adding these pressure gradients, we get the total pressure gradient as 6.85 kilopascal per meter. The numerical examples discussed here are only to illustrate the methods, how to use the methods, and the results obtained in these examples are not meant to be used for design calculations. There may be errors in the calculations, so please do your own calculations and check. Thank you.